Is Earth the only living world in the universe? By the end of this video, you will know about 30 real planets beyond our solar system where life could survive. Each one offers a tantalizing clue to what makes a world truly habitable: the right distance from its star, the presence of liquid water, a stable atmosphere, and a climate that doesn't swing wildly. Some orbit small red dwarfs, others circle sun-like stars. A few may be ocean worlds, while others might have thick atmospheres. They all reveal just how rich and surprising the possibilities are. But the search begins with the closest known candidate of them all. What do you think it would feel like to stand on a planet orbiting our nearest stellar neighbor? Proxima Centauri b is that planet, and it orbits the closest star to our Sun. At just 4.2 light-years away, this Earth-sized world lies squarely within the habitable zone of its dim red dwarf star. That means liquid water could pool on its surface, the single most important ingredient for life as we know it. But being so close to a red dwarf comes with serious challenges. First, the planet is almost certainly tidally locked. One side always faces the star, locked in a perpetual scorching day, while the other remains in endless freezing night. Only along the thin ring between them, a strip of eternal twilight, might temperatures stay mild enough for water to remain liquid. And there is another threat. Red dwarfs are volatile. They unleash powerful flares that can strip away a planet's atmosphere over time. If Proxima Centauri b ever had a thick protective blanket, those repeated bursts of radiation may have eroded it long ago. Yet astronomers did not give up on this world. They discovered it using the radial velocity method, watching the star wobble ever so slightly from the planet's gravitational pull. That tiny signal revealed a world with a mass at least 1.3 times that of Earth. It was a landmark find. Finally, we had a nearby exoplanet that looked something like home. Now, telescopes like the James Webb Space Telescope and the upcoming extremely large telescope are being designed to study such worlds in detail. They will look for atmospheric gases like oxygen or methane that could hint at biological activity. Proxima Centauri b remains one of the best targets because it is so close. If life ever arose there, we might find its fingerprints within the next decade or two. But closeness alone does not guarantee habitability. The star's flares and the planet's locked rotation mean conditions could be harsh. Still, some researchers suggest that life might adapt, perhaps surviving in the twilight zone or even beneath an ocean of liquid water. We simply do not know yet. Proxima Centauri b teaches us an important lesson. Proximity is not everything. Other nearby star systems also hold promising candidates, and each one adds a new piece to the puzzle. So now let us turn our gaze to a system that boasts not one but several potential havens for life. 40 light-years away, a remarkable system holds 7 Earth-sized worlds. This is the TRAPPIST-1 system, named after the small ultra-cool dwarf star at its center. Among its 7 planets, one stands out as an especially promising candidate for life. TRAPPIST-1e sits right in the middle of the habitable zone, receiving almost exactly the same amount of starlight as Earth receives from our Sun. That is a rare and valuable alignment. The planet is also very close in size to Earth, and measurements of its density suggest it has a solid rocky surface rather than a gaseous envelope. All of these clues point toward a world where liquid water could persist on the ground. Astronomers have studied the entire TRAPPIST-1 system intensely using both the Spitzer Space Telescope and the James Webb Space Telescope. They have measured the planet's masses and radii with impressive precision. Their observations have revealed that TRAPPIST-1e is likely the most Earth-like of the 7. It may have an atmosphere, though its composition remains unknown. Perhaps its surface is covered with oceans or continents, or maybe it is a dry, barren world. The next step is to catch its atmosphere as it passes in front of its star, a method called transmission spectroscopy. If Webb detects molecules like water vapor, carbon dioxide, or even a surprising amount of methane, our understanding of this world will transform overnight. But TRAPPIST-1e is not alone in its system. Another planet in the same family orbits just a little farther out, and it too may hold secrets worth investigating. That other world is TRAPPIST-1f, a planet that sits just a little farther from its star than its neighbor E, yet remains firmly inside the habitable zone. It receives less starlight than Earth does, but still enough that liquid water could exist on its surface. And that is where things get interesting. Several studies suggest that TRAPPIST-1f might be a global ocean world, a planet completely covered in water with no dry land at all. Imagine a sphere of endless dark liquid stretching from pole to pole, with waves driven by the gravitational pull of its nearby sibling planets. Such a world would be unlike anything in our own solar system, and it raises a thrilling possibility. Life could thrive in those deep oceans, perhaps near hydrothermal vents on the seafloor or in the sunlit layers near the surface. The ingredients for life, carbon, hydrogen, oxygen, and nitrogen, are abundant in water. And without land to break up the ocean, currents could circulate nutrients globally, creating a stable environment for microbes to evolve. But there is a catch. We do not yet know what kind of atmosphere TRAPPIST-1f possesses. If it has a thick blanket of greenhouse gases like carbon dioxide, the planet could be warmer than expected, perhaps even too warm for comfort. On the other hand, if it has little to no atmosphere, the ocean might freeze over or evaporate into space. The James Webb Space Telescope has already started to analyze the light passing through the atmospheres of planets in the TRAPPIST-1 system. Early results are still coming in, but scientists are especially eager to study F because its larger distance from the star makes it less vulnerable to the intense flare activity that affects the inner worlds. A thick atmosphere could trap heat and maintain liquid water, even with less sunlight. That makes TRAPPIST-1f a fascinating laboratory for understanding how habitable conditions might vary within a single star system. What makes this system so valuable for science is the chance to compare sibling planets that formed from the same disk of gas and dust, yet evolved in different orbits. TRAPPIST-1e and F sit at slightly different distances, receiving different amounts of energy. By studying both, astronomers can test how small changes in distance affect a planet's climate, atmosphere, and potential for life. It is like having two versions of Earth, one closer to the Sun and one a little farther out, both offering clues about the edges of habitability. If F turns out to be a water world with a stable atmosphere, it would suggest that life could exist on many planets just beyond the traditional habitable zone. If it is a frozen desert, that would tell us the zone is narrower than we thought. Either way, the comparison pushes our understanding forward. Now we leave the TRAPPIST-1 system and travel to a different kind of star, one much brighter and hotter than the dim red dwarfs we have seen so far. This next world orbits a sun-like star, and it may hold a surprise that changes how we think about living beyond Earth. 1,400 light-years away, a planet orbits a star almost identical to our Sun. This world, Kepler 452b, captured the public imagination like few others. It circles its star once every 385 days, just 20 days longer than Earth's year. Its radius is about 1.6 times larger than Earth's, placing it in the category known as super-Earths, rocky worlds bigger than our own but smaller than gas giants. The star itself is a G-type, the same class as the Sun, but it is 6 billion years old, roughly 1.5 billion years older than our star. That extra age matters. Kepler 452b has been baking in its star's light for a very long time. Astronomers suspect it may have once been a wet world, perhaps with oceans and clouds. But over billions of years, the slow intensification of its aging star could have driven away much of that water through a runaway greenhouse effect. If that happened, the planet might now be a hot, steamy world with a thick carbon dioxide atmosphere or even a dry desert. We cannot say for sure. What we do know is that Kepler 452b sits squarely inside the habitable zone, the region where liquid water could exist on the surface. Its discovery in 2015 made headlines around the world because it seemed to offer the closest match yet to a second Earth. The public excitement was real and understandable. Here was a planet roughly the same size as Earth, orbiting a sun-like star at the right distance and at just the right temperature. It felt familiar. Yet the uncertainty around its atmosphere and water history reminds us that size and location are only part of the story. A planet can look Earth-like from afar and still be profoundly different up close. Kepler 452b taught us that finding true Earth twins requires more than matching numbers. We need to understand climate evolution and long-term stability. The search continues, and the next candidate takes us to a star that is anything but Sun-like. 500 light-years away, a planet made history by proving that Earth-sized worlds could exist in the habitable zones of other stars. That world is Kepler 186f, and when astronomers announced its discovery in 2014, it marked a turning point in the search for life beyond our solar system. Before Kepler 186f, we had found larger planets in the habitable zone, but none that were truly close to Earth in size. This planet finally showed us that small rocky worlds could orbit at the right distance for liquid water. Its radius is about 1.1 times that of Earth, making it a near twin in terms of physical scale. But the similarities quickly diverge when you look at its star. Kepler 186f orbits an M-dwarf, a red dwarf star that is much cooler and dimmer than our Sun. That means its habitable zone lies much closer in, and the planet completes one orbit every 130 days. Its year is less than half of ours. Because the star is so dim, the planet receives only about 1/3 of the energy that Earth gets from the Sun, placing it near the outer edge of the habitable zone. That raises a fascinating question. Could liquid water still exist on its surface, or is it a frozen world? The answer depends on its atmosphere. A thick blanket of greenhouse gases like carbon dioxide or methane could trap enough heat to keep water from freezing. Without such an atmosphere, Kepler 186f might be a cold desert world with ice covering its oceans. Another challenge comes from the star itself. Red dwarfs are known for their powerful flares, which can strip away a planet's atmosphere over time. And because the habitable zone is so close, Kepler 186f is almost certainly tidally locked, meaning one side always faces the star while the other faces away. That locked rotation could create extreme temperature differences, but it does not rule out life. Some researchers suggest that the twilight zone between day and night might offer a stable temperature band where conditions remain mild. Despite these uncertainties, the discovery of Kepler 186f was a landmark achievement. It confirmed what many had suspected: Earth-sized planets are common in the galaxy. Before this find, we had only hints and statistical probabilities. Now we had a real example, a proof of concept that small rocky worlds could indeed reside in the habitable zones of other stars. That single discovery encouraged astronomers to keep searching, and it reshaped how we think about the potential for life. Since then, we have found many more Earth-sized candidates, each one adding to a growing catalogue of possibilities. The next planet on our list orbits a red dwarf too, but it brings something entirely different to the table, a world that challenges our assumptions about what a habitable planet can look like. There is a world just 12 light-years away that might finally give us clear answers. Lytton B orbits a red dwarf known as Lytton star, and this star is unusually calm. Most red dwarfs are prone to violent flares that could strip away a planet's atmosphere, but Lytton star shows almost none of that chaotic activity. That makes its planets far more likely to hold onto the blankets of gas needed to keep conditions stable. Titan B itself is a super-Earth about 2.5 times the mass of our own planet. It sits in the optimistic habitable zone, the region where liquid water could exist on its surface if the atmosphere is thick enough. Because the star is so quiet, the planet probably does not suffer from the tidal locking extremes seen around more volatile red dwarfs. Scientists think its rotation might be more like Earth's, with a proper day and night cycle that helps regulate temperature. That simple difference could be enormous. A stable climate, a calm star, and the right size all point toward a world where life could take hold. And because Titan B is only 12 light-years away, it is one of the closest habitable zone candidates we know. Telescopes like the James Webb Space Telescope and the upcoming extremely large telescope can study its atmosphere in detail, looking for water vapor, oxygen, or methane. Those are the chemical fingerprints of biology. If we find them, we may have discovered our first confirmed living neighbor. If not, the data will still teach us about the conditions that allow atmospheres to survive around red dwarfs. Titan B represents our best chance yet for a detailed follow-up study, but not every promising world fits neatly into our expectations. Some planets push the boundaries of what we consider habitable, forcing us to ask a deeper question. Could life exist on a world that seems completely unlike Earth? Kepler 62f is one world that challenges our assumptions. It sits 1,200 light-years away, orbiting a K-dwarf star, a type that burns steadily and calmly, more stable than the volatile red dwarfs we have discussed. The planet itself is about 40% larger than Earth, making it a super-Earth, and it lies squarely within the habitable zone of its star. That simple fact puts it on the short list of places where life could survive. But what kind of world is Kepler 62f? The answer depends on its atmosphere. If that atmosphere is thick with water vapor, the planet could be a global ocean, a water world with no land, just endless liquid stretching from pole to pole. If its atmosphere is thinner and drier, Kepler 62f might be a rocky world with frozen polar ice caps and liquid water only near the equator. Either scenario offers a habitable environment, though the character of that environment would be profoundly different. What makes this planet especially promising is its star. K-dwarfs are a sweet spot in the search for life. They are smaller and cooler than the Sun, so the habitable zone is closer in. That means planets orbit with shorter years, making them easier to detect. But unlike M-dwarfs, K-dwarfs rarely flare with dangerous bursts of radiation. Their stability means a planet like Kepler 62f could hold onto its atmosphere for billions of years, giving life plenty of time to emerge and evolve. The Kepler telescope, before it was retired, gathered enough data on this system to mark it as one of the most promising candidates in its entire mission. When astronomers look for worlds that could be truly Earth-like, they often point to Kepler 62f as a gold standard example. Its size, its orbit, its star type all combine to create a compelling case. But the planet is not perfect. Its exact composition remains unknown. We cannot yet tell if it has continents or oceans, ice caps or clouds. Those mysteries keep the scientific community eager for the next generation of telescopes. Observatories like the James Webb Space Telescope are already being pointed at such targets, and follow-up studies in the coming years could reveal whether this faraway world is covered in water or wrapped in ice. Now, not every candidate in our list fits the same mold. Some planets surprise us with conditions that seem hostile at first glance but might still harbor life in unexpected ways. One such world wears an atmosphere so thick and strange it challenges everything we thought about habitable planets. Kepler 442b sits 1,100 light-years away, and it checks nearly every box for habitability. This super-Earth orbits a K-dwarf star, a type that is smaller and cooler than our Sun, but far more stable than the volatile red dwarfs we have encountered. The planet receives about 70% of the sunlight Earth does, which places it squarely within the habitable zone where liquid water can exist on the surface. Its size is roughly 1.3 times that of Earth, and measurements of its density strongly suggest a rocky composition much like our own world. That combination of size and makeup gives it a high Earth Similarity Index, a numerical score that astronomers use to rank how closely a planet resembles our home. Kepler 442b consistently scores among the very top candidates. Scientists believe that liquid water could persist on its surface across vast regions, perhaps even forming oceans and clouds. Its star is calm and long-lived, meaning the planet has enjoyed a stable climate for billions of years, time enough for life to emerge if the conditions are right. But Kepler 442b is not the only promising world we have found. Sometimes a single star system contains multiple planets that all fall within the habitable zone, offering a rare chance to compare sibling worlds born from the same cosmic material. That kind of system provides an extraordinary laboratory for understanding how small differences in orbit can shape a planet into a living world or a barren one. Some star systems offer more than one candidate. 23 light-years away, a triple star system holds a world that orbits near the inner edge of the habitable zone. This planet is Gliese 667cc, a super-Earth circling the M-dwarf star Gliese 667c, the smallest and coolest member of a trio of stars that dance around each other. From the planet's surface, the sky would be extraordinary. Two distant companion stars would shine like brilliant points of light, one perhaps visible during the day, the other at night, creating a celestial spectacle unlike anything we see from Earth. But that beauty comes with a scientific challenge. Triple star systems are complex gravitational environments. For a planet to remain in a stable orbit for billions of years, its path must avoid the disruptive pull of the other two stars. Computer simulations suggest that Gliese 667cc does manage this, staying safely locked in orbit around its parent star without being flung away or having its orbit twisted into an extreme ellipse. Still, the presence of multiple stars means the planet's climate may experience subtle variations over long timescales as the stars shift positions and alter the amount of light reaching the world. That is a fascinating detail for researchers. It means Gliese 667cc receives about 90% of the light Earth gets from the Sun, placing it near the inner edge of the habitable zone where temperatures could be warm but still allow liquid water. If the planet has a thin atmosphere, it might be toasty. If it has a thick one, the greenhouse effect could push it into a runaway hothouse. But the planet's proximity to Earth, just 23 light-years, and the relative brightness of its host star make it an excellent target for follow-up observations. Telescopes like the James Webb Space Telescope can study the starlight filtering through its atmosphere, searching for water vapor, carbon dioxide, or other gases that hint at a living world. Astronomers consider Gliese 667cc one of the most promising candidates for such studies, simply because it is close enough and bright enough to reveal its secrets. And it is not the only planet in this system. Gliese 667c also hosts another world that orbits a little farther out, a planet that adds even more intrigue to this already remarkable neighborhood. That second world, designated Gliese 667ce, sits farther from its star than its sibling CC. While CC orbits near the warm inner edge of the habitable zone, C traces a path much farther out where sunlight is dimmer and temperatures drop. Without some form of greenhouse warming, any water on its surface would almost certainly be locked in ice, but that does not eliminate it from our list of candidates. A thick atmosphere rich in carbon dioxide or methane could trap enough heat to keep at least part of the planet liquid, especially if the atmosphere is dense enough to create a strong greenhouse effect. The question is whether such an atmosphere could survive around a red dwarf star, which we know can strip away gas over time. This uncertainty places C in a category of planets that are possible but not probable. Astronomers call these marginal candidates, and they are incredibly valuable because they help define the edges of what we consider habitable. They push us to ask tough questions. How much greenhouse gas is too much? How little starlight can a planet receive and still support liquid water? C is a test case for those very limits. But there is another layer of complexity. The exact number of planets orbiting Gliese 667c is still a matter of active debate. When the system was first studied, researchers announced they had detected up to 7 planets, including C. Later reanalysis of the data suggested that at least 2 of those signals were false positives, caused by the star's own magnetic activity rather than orbiting worlds. Today, the scientific community is divided. Some argue the system holds only 3 confirmed planets, while others believe there are 5 or even 6, including C. The signals are incredibly faint, barely above the noise of the instruments. Confirming them requires years of careful observation, multiple telescopes, and statistical models that separate planetary wobbles from stellar noise. C itself is a particularly difficult case because its signal is among the weakest. Many researchers consider it a strong candidate but not a confirmed world. This ongoing uncertainty highlights something important. M-dwarf systems are rich and complex. They can host multiple planets in tight orbits, but detecting them all pushes our technology to its limits. Each new discovery teaches us more about how to interpret the data and what to expect from these common stars. What Gliese 667c demonstrates is the sheer abundance of planets around red dwarfs. These small, dim stars make up about 75% of all stars in the galaxy. If even a fraction of them host Earth-sized worlds in their habitable zones, the number of potential homes for life could be staggering. The Gliese 667 system, with its multiple candidates, is a microcosm of that potential. C reminds us that not every promising world will be an obvious Earth twin. Some are cold and cloudy, hanging on the very edge of possibility, and yet they still deserve our attention. They force us to refine our methods and broaden our expectations. Now it is time to leave the dim glow of red dwarfs behind and travel to a star that shines much brighter, a star that is far more like our own sun. There, a planet awaits that could finally give us the clear, unambiguous signal we have been searching for. 42 light-years away, a star slightly cooler and dimmer than our Sun holds a planet that scientists cannot stop debating. This world, HD 40307G, orbits a K-dwarf star, a type known for its steady long life and mild temperament. The planet itself is a super-Earth, roughly 7 times the mass of our own world, and it completes one orbit every 200 days. That places it squarely within the habitable zone, the region where temperatures could allow liquid water to pool on the surface. It was discovered using the radial velocity method, which measures the tiny wobble the planet causes in its parent star. That wobble is small, incredibly small, but sensitive instruments have picked it up. The signal suggests a world massive enough to hold onto a thick atmosphere. That atmosphere could trap heat, perhaps keeping the surface warm enough for liquid water, even if the planet receives less starlight than Earth does. Its orbital period of 200 days puts it in a temperate zone, not too close to the star where water would boil away, not too far where it would freeze. But HD 40307G is not without its skeptics. Some researchers have reanalyzed the data and argued that the signal might not be a planet at all. It could be caused by the star's own rotation or magnetic activity, mimicking the gravitational tug of an orbiting world. The planet sits in a crowded system already known to host several other worlds, and separating all those signals from stellar noise is notoriously difficult. This controversy matters because it highlights a critical step in the search for life. Discovery alone is not enough. Every candidate must be confirmed through multiple independent observations and instruments. Without that verification, we risk chasing shadows. The scientific community is working to do exactly that, using both newer telescopes and refined analysis techniques to either confirm HD 40307G or rule it out. If confirmed, it would join a short list of promising targets for atmospheric study. Its distance is manageable, its star is bright, and its orbit sits in a sweet spot for follow-up investigations. But if it turns out to be a false alarm that is still valuable, it sharpens our tools and teaches us how to avoid similar mistakes on future searches. Every candidate, whether real or not, pushes the field forward, and the next world on our list teaches a different kind of lesson, one about how a planet personality, its shape and path through space, can affect habitability in ways that are easy to overlook. The first planet Kepler ever confirmed in the habitable zone was Kepler 22b, 600 light-years away. Its discovery in 2011 felt like a triumph. Finally, we had direct evidence that the habitable zone was not just a theoretical concept but a real region where planets could dwell. But as astronomers analyzed the data, a more complicated picture emerged. Kepler 22b has a radius roughly 2.4 times that of Earth, putting it into a category known as sub-Neptune. That size is a problem. A planet that large is likely enveloped in a thick atmosphere of hydrogen and helium, a gaseous blanket hundreds of kilometers thick. If that is the case, the surface below that atmosphere might be a crushing high-pressure world with no solid ground, a mini Neptune rather than a super-Earth. But there is another possibility. Kepler 22b could be a water world, a planet where a deep global ocean covers the entire surface, with maybe a few small islands or none at all. A thick atmosphere of steam and water vapor would explain its size. The difference between these two scenarios is enormous. A mini Neptune would offer no surface for life as we know it. A water world, however, could host microbial life in its oceans. The problem is that our data cannot distinguish between them. The Kepler telescope measures only the planet radius and orbital period. It cannot tell us what lies beneath the clouds. That uncertainty forced astronomers to rethink how they interpret habitable zone candidates. Just because a planet sits at the right distance and has the right size does not mean it is truly Earth-like. Some worlds are simply too big, holding onto thick gaseous envelopes that smother any chance of a solid surface. Kepler 22b taught us a vital lesson. Habitability is not a simple checklist. It depends on a planet's composition and history, and those details remain hidden until we can study its atmosphere. The search for life had to become more careful, more patient, and more focused on worlds where we can actually see the air they breathe. That brings us to a different kind of planet, one where we have finally confirmed the presence of an atmosphere and can begin to ask deeper questions about what lies within it. 2,700 light-years away, another world tests our understanding of what habitability really means. Kepler 69c orbits a G-dwarf star, the same type as our Sun, and it sits within the habitable zone where liquid water could exist on the surface. It receives about 80% of the sunlight Earth does, a level that would keep temperatures mild if the planet has the right atmosphere. But here is where things get complicated. Kepler 69c is roughly 70% larger than Earth, placing it in a gray zone between super-Earth and mini-Neptune. That size means its composition is a mystery. It could be a rocky world with a thin atmosphere and perhaps oceans or continents. Or it could be a world smothered in a thick envelope of hydrogen and helium with no solid surface at all, just a crushing, gaseous interior. Astronomers call this the radius gap problem. Many planets between 1.5 and 2.5 times Earth size appear to be either rocky or gaseous, with very few in between. Kepler 69c falls right in that ambiguous region, and we cannot tell which category it belongs to without studying its atmosphere. The challenge is that the planet is very far away, and its star is relatively dim at that distance, making follow-up observations difficult. Even the James Webb Space Telescope would have a hard time capturing the thin signature of its atmosphere. So for now, Kepler 69c remains a tantalizing question mark. It reminds us that the search for life is not just about finding planets at the right distance. It is about understanding their true nature, their mass, their density, their air. And that is why the next generation of telescopes and missions is so important. One such mission, TESS, the Transiting Exoplanet Survey Satellite, has already begun scanning the sky for planets around bright nearby stars. Unlike Kepler, which stared at a single patch of sky for years, TESS covers almost the entire sky, searching for worlds close enough that we can study them in detail. Its discoveries are already reshaping our list of the most promising candidates. Among TESS' first major finds was a world called TESS 700d, 100 light-years away. This planet made history because it became the very first Earth-sized exoplanet discovered by the TESS mission that sits in the habitable zone. Its radius is about 1.2 times that of Earth, placing it squarely in the category of rocky worlds that could support liquid water on their surfaces. The planet completes one orbit every 37 days, a much shorter year than ours because its star is a cool red dwarf. That dim star means the habitable zone lies very close in, and TESS 700d sits right at the sweet spot. But being so close to its star comes with a familiar consequence. The planet is almost certainly tidally locked. One side always faces the star, locked in permanent daylight, while the other side remains in endless night. Only the thin ring between them, the twilight zone, might offer temperatures mild enough for water to remain liquid. What sets this world apart from many other red dwarf candidates is its star. Most M-dwarfs are volatile, unleashing powerful flares that can strip away a planet's atmosphere. But TESS 700's star is unusually quiet. Observations show very low flare activity, meaning TESS 700d has a much better chance of holding onto the blanket of gases needed to keep its climate stable. That combination, the right size, a stable star, and a position in the habitable zone, makes TESS 700d one of the most promising targets for follow-up study. The James Webb Space Telescope could soon analyze the light passing through its atmosphere, searching for water vapor, carbon dioxide, or even the faint signatures of life. And TESS has only just begun its survey. Another discovery by this mission brings us to a world that orbits a star so calm it might be the perfect place to test our theories about habitability. The same system that gave us TESS 700d holds another promising world. Astronomers call it TESS 700e, and it orbits the same quiet red dwarf star. This planet is slightly smaller than its sibling, with a radius almost exactly the same as Earth's. That size strongly suggests a rocky composition, perhaps with a thin atmosphere or no atmosphere at all. What makes this discovery so valuable is the simple fact that two planets in the same system both sit inside the habitable zone. TESS 700d lies closer to the star, while TESS 700e orbits a little farther out. That small difference in distance allows scientists to compare them directly, studying how a planet's temperature and radiation exposure change with just a modest shift in orbit. If both worlds turn out to be rocky and capable of holding onto liquid water, it would suggest that habitable conditions can exist across a wider range of distances than we once thought. If only one of them proves capable of supporting life, that comparison will help us understand the subtle thresholds that separate a living world from a dead one. The Transiting Exoplanet Survey Satellite, a space telescope designed to scan the entire sky for nearby planets, made this discovery possible. It found both TESS 700d and E by watching for the tiny dips in starlight as the planets crossed in front of their star. That technique works best when stars are bright and close, and TESS 700 is both. Because the system lies just 100 light-years away, follow-up telescopes can study its planets in great detail. Already, astronomers have used ground-based observatories to confirm the orbits and refine their sizes. The James Webb Space Telescope may soon add its gaze, searching for water vapor or carbon dioxide in the atmospheres of these two worlds. The chance to study two potentially habitable planets in one system is a gift. It moves us beyond single candidate hunts toward comparative planetology, a field that reveals how different conditions shape different outcomes. As we build our understanding of these nearby worlds, we also prepare for the next great leap, a planet orbiting a star that is nothing like the small, calm embers we have been examining. That star shines much larger and brighter, and the planet circling it might hold the most profound surprise of all. 300 light-years away, a hidden world waited to be found. Kepler 1649c orbits a red dwarf star, and it is one of the closest matches to Earth we have ever seen. Its radius is just 1.06 times that of our planet, making it nearly identical in size. And it receives about 75% of the starlight Earth gets from the Sun, a level that could easily support liquid water on its surface if the atmosphere is right. What makes this discovery even more remarkable is that astronomers almost missed it entirely. When the Kepler Space Telescope first scanned this patch of sky, its data was processed by automated algorithms designed to catch the telltale dip in brightness as a planet crosses its star. But the signal from Kepler 1649c was weak, buried in noise, and the computer program simply overlooked it. It took a second look by human eyes years later to spot the faint pattern that had been hiding in plain sight. That moment of rediscovery turned a forgotten day to point into one of the most promising candidates for life beyond Earth. Because of its size and the amount of light it receives, Kepler 1649c is often described as an Earth analog, a world that could very well mirror our own in terms of surface temperature and the potential for oceans. But there is a catch. Its star is a red dwarf, a type known for violent flares that can strip away a planet's atmosphere over time. If Kepler 1649c ever had a thick blanket of air, those repeated bursts of radiation may have eroded it long ago. Still, some researchers argue that life could adapt. Perhaps the planet holds onto a thin but stable atmosphere made of heavier gases like carbon dioxide, or maybe it has a magnetic field strong enough to deflect the worst of the flares. We simply do not know yet. What we do know is that Kepler 1649c sits in the habitable zone, receives the right amount of energy, and is the same size as Earth. That combination is rare and precious. It pushes this world to the top of the list for follow-up observations. And while it is 300 light-years away, that distance is not too far for the next generation of telescopes. The James Webb Space Telescope could already detect its atmosphere if conditions are right. But for now, Kepler 1649c remains a promise, a world that might be our closest twin, hidden until we were ready to see it. Its story reminds us that even in data we have already collected, new discoveries are waiting, and the next planet on our list was not hidden at all. Its signal came through loud and clear, making it one of the most confidently detected candidates for life in the entire galaxy. Not every promising world captures headlines. Some sit quietly in the data, waiting for patient eyes to appreciate their worth. Kepler 1410b is one of those quiet gems, a super-Earth about 1.2 times the size of our own planet. It orbits a K-dwarf star, a type that glows steadily and lives for tens of billions of years, far longer than our Sun ever will. That longevity matters. It means the planet has enjoyed a stable source of energy for a very long time, giving any potential life forms ample opportunity to arise and evolve. The planet sits squarely inside the habitable zone, where temperatures allow liquid water to exist on the surface. Its equilibrium temperature, the temperature the planet would have if it had no atmosphere, is strikingly similar to Earth's own. That does not guarantee warmth. A planet with no atmosphere would be a frozen desert, but it does suggest that if Kepler 1410b possesses even a modest blanket of greenhouse gases, it could be quite comfortable. Its radius and estimated mass hint at a rocky composition, perhaps with a solid surface and a thin atmosphere. We cannot be certain without more data, but the clues are promising. What makes Kepler 1410b valuable is not fame. It is not the closest or the most Earth-like in size. It is instead a representative of the wider population of potentially habitable worlds. Most of the planets we discover are not headline makers. They are ordinary, unassuming, and common. By studying many such worlds, astronomers learn to separate the typical from the exceptional. They ask how many planets at this size actually have atmospheres, how many retain liquid water over geological timescales. Kepler 1410b is a test case for those questions. Its star is bright enough for follow-up observations with the James Webb Space Telescope, though the planet is far enough away that those observations will be challenging. Still, the effort is worthwhile because every data point fills a gap in our understanding. The quiet ones teach us about the full range of possibilities. Some habitable zone worlds may be ocean-covered. Others may be dry deserts with thin carbon dioxide atmospheres. A few might hold exactly the right mix of gases to support life. Kepler 1410b reminds us that the search for life is not about finding a single perfect twin. It is about mapping the diversity of conditions across the galaxy. That diversity becomes even more striking when we consider planets around stars that are nothing like the dim K dwarfs we have been discussing. Some stars burn hotter, brighter, and faster, and their planets face a completely different set of challenges. Some worlds hide their true nature behind a veil of uncertainty. 850 light-years away, a planet called Kepler 440b orbits a K-dwarf star, a steady type that burns for billions of years. Its radius is about 1.9 times that of Earth, placing it in the super-Earth category, larger than our planet but smaller than gas giants. It sits inside the habitable zone, the region where liquid water could exist on a surface. But that size raises a crucial question. A planet that large might not be rocky at all. It could have retained a thick envelope of hydrogen and helium, the lightest and most abundant gases in the universe. If that is the case, Kepler 440b would be a mini Neptune, a world with a crushing atmosphere and no solid ground, a place where life as we know it would struggle to survive. Yet there is another possibility. The planet could be a water world, a globe covered entirely by a deep ocean with perhaps a few scattered volcanic peaks. In that scenario, the hydrogen and helium would be minimal, and the planet's surface would be liquid water, warm and stable enough to host microbial life. The difference between these two fates depends entirely on the planet's mass. If Kepler 440b is dense and heavy, it is likely rocky with a thin atmosphere. If it is light and puffy, it is a gas dwarf. Astronomers have not yet measured its mass precisely, and that missing piece of data keeps the mystery alive. The planet was discovered by the Kepler Space Telescope using the transit method, which reveals only its size and orbital period. To know its true nature, we need to measure how much it tugs on its star, a technique called radial velocity. That requires sensitive instruments and many hours of observation. For now, Kepler 440b remains a tantalizing unknown, a world that could be a watery paradise or a gaseous ghost. It reminds us that size alone is not enough, and that the search for life demands patience and deeper investigation. But not every planet keeps its secrets so quietly. Some worlds reveal their character through the shape of their path, swinging through their habitable zones in ways that defy expectations. 470 light-years away, a planet raises a troubling question. Kepler 438b is nearly identical to Earth in size, with a radius just 1.12 times our own. It orbits a red dwarf star and lies squarely within the habitable zone, the region where liquid water could gather on its surface. In many ways, it looks like an ideal candidate, but there is a catch. This world receives about 40% more sunlight than Earth does, which already pushes its surface temperatures toward the warmer side. More importantly, its star is notoriously violent, unleashing powerful flares at a rate far higher than most other red dwarfs. Those flares send bursts of radiation hurtling toward the planet, energy that can strip away a fragile atmosphere over time. Even if Kepler 438b once had a thick blanket of air, repeated exposure to those stellar storms may have left it barren and exposed. Astronomers rank this world very high on the Earth Similarity Index, a numerical score that compares a planet to our own. But when they calculate their confidence in its actual habitability, the number drops sharply. That gap between appearance and reality is a crucial lesson. Location alone, being at the right distance from a star, is not enough. A planet also needs a stable, long-lived host that does not threaten its atmosphere with constant eruptions. Kepler 438b teaches us that even a seemingly perfect Earth twin can be rendered hostile by the temperament of its star. The search for life demands we look beyond simple checklists and ask harder questions about the true conditions on these distant worlds. And that is precisely why astronomers now turn their attention to a different kind of star, one that burns with far greater patience and predictability, offering its planets a chance to keep their atmospheres safe for billions of years. Another world that tests our ability to categorize sits 600 light-years away. Kepler 61b orbits a K-dwarf star, a type known for its steady, long-lived glow. The planet itself is about 2.1 times the radius of Earth, placing it squarely in the super-Earth category, but that size opens a question. A world this large could be a rocky planet with a thick atmosphere and perhaps global oceans, or it could be a mini Neptune, a small gas planet wrapped in a crushing envelope of hydrogen and helium. Astronomers cannot tell which from the transit data alone. The Kepler telescope measured the dip in starlight as the planet crossed its star, revealing its size and its orbital period of just 59 days. That short orbit puts Kepler 61b near the inner edge of the habitable zone, where temperatures could allow liquid water if the atmosphere is right. But the uncertainty around its composition means we are guessing. If it is a water world, its surface might be a deep ocean with no land, a place where life could thrive in the sunlit layers. If it is a mini Neptune, any solid surface would be buried under thousands of kilometers of gas with pressures that would crush anything we know. This planet is a perfect example of the limits we still face. Even when we detect a world at the right distance and with the right size, we often lack the data to know its true nature. The next steps require measuring its mass, which would tell us its density, and from that, its likely composition. That takes time, patience, and telescopes designed for precise radial velocity measurements. Until then, Kepler 61b reminds us that the search for life is full of uncertainties. Each candidate teaches us what we still need to learn, and that is exactly why astronomers are turning to a different approach, one that uses a technique that can reveal a planet's mass directly from the tiny wobble of its star. Some planets reveal themselves slowly, their signals buried in years of data from telescopes that never stop watching. K272e is one of those worlds, a super-Earth 217 light-years away that was discovered during the extended K2 mission of the Kepler Space Telescope. Its star is a dim red dwarf, small and cool, and the planet completes one orbit every 18 days. That might sound impossibly fast, but because the star is so faint, the habitable zone lies very close in, and 18 days places this world right at the right distance for liquid water to exist on its surface. The planet is about 1.4 times the size of Earth, making it a super-Earth, a rocky world with a solid surface underneath whatever atmosphere it may hold. Its position in the habitable zone is well established, but the star is an M-dwarf, and we know the challenges that come with that. Flares, tidal locking, and the slow erosion of atmospheres all threaten the long-term habitability of such worlds. Still, K272e stands out because its orbit is well measured, and its size suggests a rocky composition. Astronomers consider it a strong candidate for follow-up studies, precisely because it is not too far away and its star is relatively bright for its type. The James Webb Space Telescope could potentially analyze the starlight filtering through its atmosphere if the planet has one thick enough to detect. That is the key question now. Does this world hold onto a blanket of gas, or has its star stripped it bare over billions of years? The answer could come within the next few years as telescopes gather more data on this and similar worlds. Each such measurement inches us closer to understanding how common habitable conditions truly are in the galaxy. And from here, the search continues with another world that orbits a star with surprising stability, offering yet another chance to test our theories of habitability. 4.2 light-years away, the closest star to our Sun holds a planet that could rewrite everything we know about life beyond Earth. Proxima Centauri b is an Earth-sized world, almost exactly the same radius as our own, and it orbits a dim red dwarf star at a distance where liquid water could exist on its surface. That single fact makes it one of the most intensely studied exoplanets in history. Astronomers discovered it using the radial velocity method, watching the star wobble ever so slightly as the planet tugged on it gravitationally. The signal was faint, barely above the noise, but clear enough to reveal a world with a mass at least 1.3 times that of Earth. It was a landmark moment. For the first time, we had a nearby candidate just 4.2 light-years away that looked like a possible second home. But being close does not mean being comfortable. Proxima Centauri b sits in the habitable zone of its star, the region where temperatures could allow liquid water to pool on the surface. However, red dwarfs are volatile. They unleash powerful flares that can strip away a planet's atmosphere over time. If this world ever had a thick blanket of air, those repeated bursts of radiation may have eroded it long ago. And there is another challenge. The planet is almost certainly tidally locked, meaning one side always faces the star in perpetual daylight while the other remains in endless night. Only along the thin ring between them, a strip of eternal twilight, might temperatures stay mild enough for water to remain liquid. These obstacles do not eliminate the possibility of life. Some researchers suggest that microbial organisms could survive beneath an ocean of liquid water, shielded from flares, or in the twilight zone where temperatures remain stable. Others argue that if the planet has a magnetic field strong enough to deflect radiation, its atmosphere might hold on much longer than we assume. The truth is, we simply do not know yet. And that uncertainty is exactly why telescopes like the James Webb Space Telescope and the upcoming extremely large telescope are being designed to study this world in detail. They will look for atmospheric gases like oxygen or methane that could hint at biological activity. If we find them, Proxima Centauri b could become the first confirmed living neighbor in human history. The intense interest in this planet is not just about its proximity. It is about what it represents. Proxima Centauri b is a test case, a proving ground for our ability to detect and characterize habitable worlds around the most common type of star in the galaxy. Red dwarfs make up about 75% of all stars. If even a fraction of them host planets like this one, the number of potential homes for life could be staggering. But Proxima Centauri b also teaches us a vital lesson. Proximity is not everything. Other nearby star systems, some just a few light years farther away, hold their own candidates with different challenges and different promises. And as we move from one world to the next, we begin to see just how rich and varied the possibilities really are. 40 light years away, a remarkable system holds 7 Earth-sized worlds. Among them, one planet stands out as the most promising candidate for life. This world is called TRAPPIST-1e, and it orbits a small, ultra-cool dwarf star at a distance that feels almost uncanny. The amount of starlight it receives is nearly identical to what Earth gets from our Sun. That places it squarely in the habitable zone, the region where liquid water can exist on a surface. And that is not the only similarity. Measurements of its size and density strongly suggest a solid rocky surface, not a gaseous envelope or a world of deep ice. Astronomers have studied the entire TRAPPIST-1 system intensely, first with the Spitzer Space Telescope and now with the James Webb Space Telescope. They have measured the planet's masses and radii with remarkable precision, and the results point to TRAPPIST-1e as the most Earth-like of the seven. It may have an atmosphere, perhaps rich in water vapor or carbon dioxide, or maybe thinner and more like our own. The next step is to catch that atmosphere as the planet passes in front of its star, using a technique called transmission spectroscopy. If Webb detects molecules like oxygen or methane, our understanding of this world will change overnight. But TRAPPIST-1e is not alone in its system. Another planet just a little farther out orbits at the edge of the habitable zone, and it too holds secrets worth investigating. That world may be covered entirely by ocean, a water world unlike anything we have seen before. TRAPPIST-1f sits just a little farther out from its star than its neighbor E, yet it remains firmly inside the habitable zone, where temperatures could still allow liquid water to exist on a surface. It receives less starlight than Earth does, but still enough to keep water from freezing if the planet has the right atmosphere, and that is where the intrigue deepens. Several studies suggest that TRAPPIST-1f might be a global ocean world, a planet completely covered in water with no dry land at all. Imagine a sphere of endless dark liquid stretching from pole to pole, with waves driven by the gravitational pull of its nearby sibling planets. Such a world would be unlike anything in our own solar system, and it raises a thrilling possibility. Life could thrive in those deep oceans, perhaps near hydrothermal vents on the seafloor or in the sunlit layers near the surface. The ingredients for life, carbon, hydrogen, oxygen, and nitrogen, are abundant in water, and without land to break up the ocean, currents could circulate nutrients globally, creating a stable environment for microbes to evolve. But there is a catch. We do not yet know what kind of atmosphere TRAPPIST-1f possesses. If it has a thick blanket of greenhouse gases like carbon dioxide, the planet could be warmer than expected, perhaps even too warm for comfort. On the other hand, if it has little to no atmosphere, the ocean might freeze over or evaporate into space. The James Webb Space Telescope has already started to analyze the light passing through the atmospheres of planets in the TRAPPIST-1 system. Early results are still coming in, but scientists are especially eager to study F because its larger distance from the star makes it less vulnerable to the intense flare activity that affects the inner worlds. A thick atmosphere could trap heat and maintain liquid water, even with less sunlight. That makes TRAPPIST-1f a fascinating laboratory for understanding how habitable conditions might vary within a single star system. The chance to compare sibling planets that formed from the same disk of gas and dust yet evolved in different orbits is rare and invaluable. TRAPPIST-1e and F sit at slightly different distances, receiving different amounts of energy. By studying both, astronomers can test how small changes in distance affect a planet's climate, atmosphere, and potential for life. It is like having two versions of Earth, one closer to the Sun and one a little farther out, both offering clues about the edges of habitability. If F turns out to be a water world with a stable atmosphere, it would suggest that life could exist on many planets just beyond the traditional habitable zone. If it is a frozen desert, that would tell us the zone is narrower than we thought. Either way, the comparison pushes our understanding forward. Now we leave the TRAPPIST-1 system and travel to a different kind of star, one much brighter and hotter than the dim red dwarfs we have seen so far. This next world orbits a sun-like star, and it may hold a surprise that changes how we think about living beyond Earth. 1,400 light-years away, a planet orbits a star almost identical to our Sun. This world is called Kepler 452b, and from the very first data it felt familiar. Its orbital period is 385 days, just 20 days longer than an Earth year. Its radius is about 1.6 times larger than Earth, placing it squarely in the super-Earth category, a rocky world that is bigger than our own but still solid. And it sits inside the habitable zone of a G-type star, the same type as the Sun. That combination of size, orbit, and stellar type made headlines around the world when it was announced in 2015. The public called it Earth's older cousin, and the name stuck. Here, finally, was a world that mirrored our own in the most important ways, but there is a twist. Kepler 452b is 6 billion years old, about 1.5 billion years older than Earth. That extra age matters. Over those long eons, its star has slowly brightened, as all sun-like stars do as they age. That gradual increase in energy could have triggered a runaway greenhouse effect, boiling away any oceans that once existed. Astronomers suspect that Kepler 452b may have started as a wet world, perhaps covered in liquid water, but over billions of years that water may have escaped into space, leaving behind a thick, steamy atmosphere of carbon dioxide and water vapor. If that scenario is correct, the planet today could be a hot, humid world with no open oceans or even a dry desert. We cannot see its surface, not directly. All we have are measurements of its size and orbit, plus estimates of its mass from radial velocity data. Those numbers point to a planet that is likely rocky, but with an atmosphere far thicker than Earth. The discovery of Kepler 452b was a landmark moment because it proved that Earth-like worlds could exist around Sun-like stars. It raised public excitement to a new level, and it pushed astronomers to ask deeper questions about what habitability really means over cosmic timescales. If a planet can start with oceans and lose them simply because its star grows brighter, then the window for life is not just about location, it is about timing. Kepler 452b stands as a reminder that even a near-perfect twin can evolve into something very different. And that lesson guides us as we turn our attention to a planet orbiting a star that could not be more different from our Sun. 500 light-years away, a different kind of discovery marked a turning point in the search for alien worlds. This planet, Kepler 186f, became the very first Earth-sized planet ever confirmed to orbit in the habitable zone of another star. Its radius is about 1.1 times that of Earth, making it a near twin in size, but its star could not be more different from our Sun. Kepler 186f orbits an M dwarf, a small dim red star that radiates much less energy than the Sun does. Because the star is so cool, its habitable zone lies very close in. The planet completes one full orbit every 130 days, less than half an Earth year. That tight orbit means the world is almost certainly tidally locked, with one hemisphere always facing the star and the other locked in perpetual night. And like all red dwarfs, this star is prone to powerful flares that could slowly strip away any atmosphere the planet might have. Only the narrow twilight ring between day and night might offer a stable temperature band where liquid water could survive. Despite these challenges, the discovery of Kepler 186f in 2014 was a landmark achievement. It confirmed what astronomers had long suspected: Earth-sized planets are common throughout the galaxy. Before this find, we had only hints and statistical probabilities. Now we had a real example, a proof of concept that small rocky worlds could indeed dwell in the habitable zones of other stars. That single discovery encouraged the entire field to keep searching, and it reshaped how we think about the potential for life beyond Earth. But even as we celebrate this first, another planet around a red dwarf was about to challenge our assumptions even further. A world that orbits a star with an unusually quiet temperament, offering a new kind of promise. 12 light-years away, a quiet red dwarf star holds a world that might be our clearest window into another living planet. This star, known as Lytton star, is unusually calm for an M-dwarf. Most red dwarfs erupt unpredictably with powerful flares that can strip away a planet's atmosphere over time, but Lytton's star barely flares at all. That steady behavior is a gift for any world orbiting close to it, and one such world, Lytton B, sits right in the middle of the optimistic habitable zone. Lytton B is a super-Earth, roughly 2.5 times the mass of our own planet. Its orbit carries it around its star in just 18 days, but because Lytton's star is so dim, that close distance still provides the right amount of warmth for liquid water to exist on its surface. Without the threat of constant stellar storms, this world has a much better chance of holding onto a thick atmosphere, a blanket of gases that could keep temperatures stable and shield the surface from harmful radiation. That atmosphere, if it exists, might be rich in water vapor, carbon dioxide, or even oxygen. The planet's proximity, just 12 light-years away, makes it one of the best targets for the next generation of telescopes. The James Webb Space Telescope can already study the starlight filtering through its atmosphere, searching for the chemical fingerprints of life. The extremely large telescope, currently under construction in Chile, will go even further, capable of directly imaging planets like Lytton B and analyzing their surface conditions. Astronomers rank it among the top candidates for these follow-up studies precisely because it is close enough and bright enough to reveal its secrets. Lytton B offers something rare, a combination of size, location, and stellar stability that makes it a credible place to search for biology. If life ever arose there, its signatures might be detectable within the next decade. But not every promising world fits this neat pattern. Some planets challenge our definition of habitability entirely, forcing us to ask whether a world can be alive in ways we have never imagined. Kepler 62f forces us to reconsider what a habitable world really looks like. 1,200 light-years away, this super-Earth circles a K-dwarf star, a type that burns steadily and calmly for tens of billions of years. The planet itself is about 40% larger than Earth, placing it in a category where composition is uncertain but promising. It sits squarely inside the habitable zone, the region where liquid water can exist on a surface. What kind of surface, though, depends entirely on its atmosphere. If that atmosphere is thick with water vapor, Kepler 62f could be a global ocean, a world completely covered in liquid with no land breaking the horizon. If the atmosphere is thinner and drier, the planet might be a rocky place with frozen polar ice caps and liquid water only near the equator. Both scenarios are possible, and both offer environments where life could take hold, though in very different ways. What makes this world especially valuable is its star. K-dwarfs are a sweet spot in the search for life. They are smaller and cooler than the Sun, so the habitable zone sits closer in, making planets easier to detect through the transit method. But unlike the volatile M-dwarfs we have discussed, K-dwarfs rarely flare with dangerous bursts of radiation. Their stable output means a planet like Kepler 62f can hold onto its atmosphere for billions of years, giving life a long, uninterrupted window to emerge. The Kepler telescope gathered enough data on this system to mark it as one of the most promising candidates in its entire mission. When astronomers compile lists of worlds that could be truly Earth-like, Kepler 62f consistently appears near the top. Its size, its orbit, and its stellar host all align to create a compelling case, but the planet keeps its deepest secrets hidden. We cannot yet tell whether it is covered in ocean or draped in ice. That mystery is precisely what drives the next generation of telescopes. Observatories like the James Webb Space Telescope are already being pointed at such targets, and follow-up studies in the coming years could reveal whether this faraway world is a watery haven or a frozen desert. Either answer would reshape our understanding of where life can survive, and that brings us to a planet with an atmosphere so thick and strange it challenges everything we thought possible. Another world, Kepler 442b, sits 1100 light-years away and offers a different kind of promise. It orbits a K-dwarf star, a type that glows steadily and calmly for tens of billions of years, providing a stable and predictable source of energy. That matters because volatile stars can strip away the very conditions life needs to survive. Kepler 442b receives about 70% of the sunlight Earth does, placing it squarely inside the habitable zone where liquid water can exist on a surface. That is not too hot for oceans to boil away and not too cold for them to freeze solid. The planet itself is about 1.3 times the size of Earth, and measurements of its density strongly suggest a rocky composition, not a gaseous envelope or a world of deep ice. All these clues add up to one of the highest Earth Similarity Index scores ever recorded, a numerical ranking that astronomers use to compare how closely a planet resembles our own home. Kepler 442b consistently appears near the very top of that list, and for good reason. Its size, its position, and the calm nature of its star all point toward a world where liquid water could pool on the surface, perhaps forming oceans or lakes, maybe even supporting a full water cycle with clouds and rain. Scientists believe it is one of the most promising candidates in the entire known catalog for hosting persistent surface liquid water. But what would that water really look like? If the planet has a thin atmosphere similar to Earth, its surface temperatures might be cool but comfortable, like a mild spring day in many parts of our world. If the atmosphere is thicker with greenhouse gases, the world could be warmer, perhaps tropical. Either way, the conditions appear to be within the range that life as we know it could tolerate. The real excitement comes from the possibility that Kepler 442b is not an isolated case. Some star systems contain multiple planets that all fall within the habitable zone, offering a rare chance to compare sibling worlds that formed from the same dust and gas yet evolved in slightly different orbits. That comparison could reveal how small changes in distance affect a planet's climate and atmosphere, and whether life can emerge on more than one world around the same star. The search for those systems is already underway, and the next candidate on our list belongs to a star that hosts not one but several worlds at the very edge of habitability. 23 light-years away, a triple star system holds a world that orbits near the edge of possibility. This planet, Gliese 667cc, circles the smallest star in a trio of suns that dance around each other in a complex gravitational ballet. It is a super-Earth with a mass roughly 3.7 times that of our own planet, making it larger and heavier than Earth but still a rocky world with a solid surface. What makes it stand out is its position. It orbits near the inner edge of the habitable zone, receiving about 90% of the light that Earth gets from the Sun. That places it in a region where liquid water could pool on its surface, but the margin is thin. If the planet has even a modest atmosphere, it could trap enough heat to keep things comfortable. But if the atmosphere is thin, the world might be too warm, perhaps even a steamy hothouse. The triple star system adds an extra layer of complexity. Two companion stars, both larger and brighter than the red dwarf Gliese 667c, orbit farther out. Their gravitational pull could, over long timescales, disturb the orbit of a planet so close to the inner star. Yet computer simulations show that Gliese 667cc manages to stay stable, its path locked in a safe resonance that avoids being flung away or pulled into an extreme ellipse. Still, the presence of multiple stars means the planet experiences subtle variations in light over thousands of years as the stars shift positions. Those changes are slow and gentle, but they hint at a climate that might not be perfectly constant. From the surface, the sky would be extraordinary. 2 additional suns, one perhaps visible during the day and the other at night, would create a celestial spectacle unlike anything we see from Earth. That beauty comes with a practical advantage for astronomers, because the planet orbits a relatively bright star in a system just 23 light-years away. It is an excellent target for follow-up studies. Telescopes like the James Webb Space Telescope can already analyze the starlight filtering through its atmosphere, searching for water vapor, carbon dioxide, or even the faint signatures of life. The next step is to measure its mass more precisely, which would reveal its density and confirm whether it is truly rocky. Gliese 667cc is a candidate that keeps giving. But it is not the only world in this system. Another planet, orbiting a little farther out, adds to the intrigue and challenges our assumptions about where life can survive. That second world orbits further from the star, where the light grows dimmer and temperatures drop. Astronomers call it Gliese 667cE, and it traces a path much farther out than its sibling CC. Without some form of greenhouse warming, any water on its surface would almost certainly be locked in ice. But that does not eliminate it from our list of candidates. A thick atmosphere rich in carbon dioxide or methane could trap enough heat to keep at least part of the planet liquid, especially if the atmosphere is dense enough to create a strong greenhouse effect. The question is whether such an atmosphere could survive around a red dwarf star, which we know can strip away gas over time. This uncertainty places C in a category of planets that are possible but not probable. Astronomers call these marginal candidates, and they are incredibly valuable because they help define the edges of what we consider habitable. They push us to ask tough questions. How much greenhouse gas is too much? How little starlight can a planet receive and still support liquid water? C is a test case for those very limits. But there is another layer of complexity. The exact number of planets orbiting Gliese 667c is still a matter of active debate. When the system was first studied, researchers announced they had detected up to 7 planets, including C. Later reanalysis of the data suggested that at least 2 of those signals were false positives, caused by the star's own magnetic activity rather than orbiting worlds. Today, the scientific community is divided. Some argue the system holds only 3 confirmed planets, while others believe there are 5 or even 6, including C. The signals are incredibly faint, barely above the noise of the instruments. Confirming them requires years of careful observation, multiple telescopes, and statistical models that separate planetary wobbles from stellar noise. C itself is a particularly difficult case because its signal is among the weakest. Many researchers consider it a strong candidate but not a confirmed world. This ongoing uncertainty highlights something important. M-dwarf systems are rich and complex. They can host multiple planets in tight orbits, but detecting them all pushes our technology to its limits. Each new discovery teaches us more about how to interpret the data and what to expect from these common stars. What Gliese 667c demonstrates is the sheer abundance of planets around red dwarfs. These small, dim stars make up about 75% of all stars in the galaxy. If even a fraction of them host Earth-sized worlds in their habitable zones, the number of potential homes for life could be staggering. The Gliese 667 system, with its multiple candidates, is a microcosm of that potential. C reminds us that not every promising world will be an obvious Earth twin. Some are cold and cloudy, hanging on the very edge of possibility, and yet they still deserve our attention. They force us to refine our methods and broaden our expectations. Now it is time to leave the dim glow of red dwarfs behind and travel to a star that shines much brighter, a star that is far more like our own sun. There, a planet awaits that could finally give us the clear, unambiguous signal we have been searching for. 42 light-years away, a star slightly cooler and dimmer than our sun holds a planet that scientists cannot stop debating. This world, HD 40307G, is a super-Earth roughly 7 times the mass of our own planet, and it orbits a K-dwarf star. That type of star is known for its steady long life and mild temperament, far less volatile than the red dwarfs we have been discussing. The planet was discovered using the radial velocity method, which measures the tiny wobble the planet causes in its parent star. That wobble is small, incredibly small, but sensitive instruments have picked it up. The signal suggests a world massive enough to hold onto a thick atmosphere. That atmosphere could trap heat, perhaps keeping the surface warm enough for liquid water, even if the planet receives less starlight than Earth does. Its orbital period of 200 days puts it in a temperate zone, not too close to the star where water would boil away, not too far where it would freeze. That 200-day orbit is significant. It means the planet experiences a moderate climate with seasons that change slowly and predictably. If HD 40307G does have liquid water, it could be a stable, long-lasting home for life to develop. But here is where things get complicated. Not everyone agrees that HD 40307G is real. Some researchers have reanalyzed the same data and argued that the signal might not be a planet at all. It could be caused by the star's own rotation or magnetic activity, mimicking the gravitational tug of an orbiting world. The planet sits in a crowded system already known to host several other worlds, and separating all those signals from stellar noise is notoriously difficult. This controversy matters because it highlights a critical step in the search for life. Discovery alone is not enough. Every candidate must be confirmed through multiple independent observations and instruments. Without that verification, we risk chasing shadows. The scientific community is working to do exactly that, using both newer telescopes and refined analysis techniques to either confirm HD 40307G or rule it out. If confirmed, it would join a short list of promising targets for atmospheric study. Its distance of 42 light-years is manageable, its star is bright, and its orbit sits in a sweet spot for follow-up investigations. But if it turns out to be a false alarm that is still valuable, it sharpens our tools and teaches us how to avoid similar mistakes on future searches. Every candidate, whether real or not, pushes the field forward. The lesson from HD 40307G is that we must be patient and rigorous. The search for life is not about declaring victory at the first promising signal. It is about building a body of evidence so strong that no reasonable doubt remains. And that is exactly why astronomers are now turning to a different kind of planet, one whose orbit follows a path so unusual that it raises entirely new questions about what it means to be habitable. 600 light-years away, the Kepler telescope discovered the first planet ever confirmed to orbit in the habitable zone of a Sun-like star. This world, Kepler 22b, made headlines for a simple reason. It proved that the habitable zone was not just a theoretical idea but a real region where planets could dwell. But the excitement was quickly tempered by a puzzle. Its radius is about 2.4 times that of Earth, placing it squarely in a category astronomers call sub-Neptune. That size means it could be a mini-Neptune, a planet wrapped in a thick envelope of hydrogen and helium with a crushing atmosphere that smothers any solid surface. If that is the case, life as we know it would have no place to stand. Yet there is another possibility. Kepler 22b might be a water world, a planet covered by a global ocean so deep that no land breaks the surface. A thick atmosphere of steam and water vapor could explain its size, and such a world could host microbial life in its sunlit layers. The problem is that we cannot tell which scenario is true from the data we have. The Kepler telescope measures only the planet's radius and orbital period. It cannot see through the clouds. That uncertainty forced astronomers to learn a hard lesson. Just because a planet sits at the right distance and has the right temperature does not mean it is truly Earth-like. Some worlds are simply too big, holding onto gaseous envelopes that hide their true nature. Kepler 22b became a cautionary tale, a reminder that finding a habitable zone candidate is only the first step. The next step is to study its atmosphere, and that requires telescopes that can capture the faint signature of light filtering through air. One such planet has already given us that gift. Its atmosphere has been confirmed, and what we found there changed everything we thought we knew about worlds beyond our solar system. 2,700 light-years away, another world tests our understanding of what habitability really means. This planet is Kepler 69c, and it orbits a G-dwarf star the same type as our Sun. It sits squarely inside the habitable zone, the region where liquid water could exist on a surface, and it receives about 80% of the sunlight Earth gets from the Sun, a level that would keep temperatures mild if the planet has the right kind of atmosphere. That all sounds promising, but here is where things get complicated. Kepler 69c is roughly 70% larger than Earth, placing it in a gray zone between super-Earth and mini-Neptune. That size means its composition is a mystery. It could be a rocky world with a thin atmosphere and perhaps oceans or continents. Or it could be a world smothered in a thick envelope of hydrogen and helium with no solid surface at all, just a crushing, gaseous interior. Astronomers call this the radius gap problem. Many planets between 1.5 and 2.5 times Earth size appear to be either rocky or gaseous, with very few in between. Kepler 69c falls right in that ambiguous region, and we cannot tell which category it belongs to without studying its atmosphere. The challenge is that the planet is very far away, and its star is relatively dim at that distance, making follow-up observations difficult. Even the James Webb Space Telescope would have a hard time capturing the thin signature of its atmosphere. So for now, Kepler 69c remains a tantalizing question mark. It reminds us that the search for life is not just about finding planets at the right distance. It is about understanding their true nature, their mass, their density, their air. And that is why the next generation of telescopes and missions is so important. One such mission, the Transiting Exoplanet Survey satellite, has already begun scanning the sky for planets around bright nearby stars. Unlike Kepler, which stared at a single patch of sky for years, this satellite covers almost the entire sky, searching for worlds close enough that we can study them in detail. Its discoveries are already reshaping our list of the most promising candidates. Among TESS' most significant finds is a world called TESS 700d. This planet sits 100 light-years away, orbiting a small red dwarf star, and it made history the moment astronomers confirmed its existence. It became the very first Earth-sized exoplanet discovered by the Transiting Exoplanet Survey satellite that lies inside the habitable zone, the region where temperatures could allow liquid water to pool on the surface. That is a milestone worth pausing over. TESS was designed to scan the entire sky, searching for planets around bright nearby stars, and TESS 700d was its first real reward in the search for potentially habitable worlds. The planet measures about 1.2 times the radius of Earth, placing it squarely in the category of rocky worlds that could support a solid surface and perhaps oceans. It completes one full orbit around its star every 37 days, a short year that keeps it very close to its parent sun. That close orbit comes with a familiar consequence. TESS 700d is almost certainly tidally locked. One hemisphere always faces the star, bathed in perpetual daylight, while the opposite side remains locked in endless night. Only the narrow ring between them, a strip of eternal twilight, might offer temperatures stable enough for liquid water to survive. But here is where this world sets itself apart from many other red dwarf candidates. Its host star is unusually quiet. Most M-dwarfs unleash powerful flares that can strip away a planet's atmosphere over time, but TESS 700 shows remarkably low flare activity. Observations from multiple telescopes confirm that this star is calm, steady, and predictable. That makes a world of difference. Without frequent violent eruptions stripping away its protective blanket, TOI 700d has a real chance of holding onto the atmosphere it may have formed with. And an atmosphere, as we have seen again and again, is the single most important factor in determining whether a planet can truly support life. If TOI 700d does have a thick blanket of air, the twilight zone between its day and night sides could be a temperate haven where liquid water gathers and conditions remain stable over billions of years. The James Webb Space Telescope is already being pointed at this system, searching for the chemical fingerprints of water vapor, carbon dioxide, or even the faint signatures that could hint at biological activity. TOI 700d is not just another candidate. It is a genuine test case, a world close enough and bright enough for detailed study, and its quiet star gives it the best possible chance of being a living world. But TESS did not stop with this single discovery. The same system that gave us this promising planet holds another surprise, a sibling world that orbits even closer to the star, and it too may hold secrets about how life can emerge in the most unexpected places. The same calm star holds another planet, even smaller and closer to Earth size. Astronomers call it TOI 700e, and it orbits the same quiet red dwarf that hosts its sibling world. This planet measures just 1.04 times the radius of Earth, making it a near twin in physical scale. Its size strongly suggests a rocky composition, a solid world with a surface that could host oceans or continents, provided it has the right atmosphere. It lies slightly farther from the star than TOI 700d, but still within the optimistic habitable zone, the region where liquid water could exist if conditions are favorable. The planet completes one orbit every 28 days, a short year that keeps it close to its dim parent star. And like its sibling, it faces the familiar challenge of tidal locking, with one side always turned toward the star and the other locked in eternal night. Yet the star's remarkable calm, its near absence of violent flares, gives both planets a fighting chance at retaining their atmospheres. That is what makes this system so precious. It offers something rare, two potentially habitable worlds orbiting the same star at slightly different distances, allowing scientists to compare them directly. By studying both TOI 700d and E, astronomers can test how a small change in orbit affects a planet's climate, its ability to hold onto water, and the long-term stability of its atmosphere. One planet might turn out to be a temperate water world while the other remains a frozen desert, or both could support liquid water. Either result teaches us something profound about the boundaries of habitability. The Transiting Exoplanet Survey satellite, TESS, made this discovery possible by scanning the entire sky for planets around bright nearby stars. Unlike the original Kepler mission, which gazed at a single patch of sky for years, TESS covers almost the whole celestial sphere, focusing on stars close enough that we can study their planets in detail with telescopes like the James Webb Space Telescope. The TOI 700 system, just 100 light-years away, is a direct result of that strategy. Its two promising worlds represent a new era in the search for life. And yet, not all promising candidates orbit such quiet stars. Some circle stars that are far more intense, blazing with a heat and light that challenge everything we assume about where life can survive. 300 light-years away, a planet nearly identical to Earth waited to be found. Astronomers call it Kepler 1649c, and its size is almost a perfect match for our own world, with a radius just 1.06 times that of Earth. It receives about 75% of the starlight that Earth gets from the Sun, placing it squarely inside the habitable zone where liquid water could pool on a surface. In many ways, it looks like one of the closest analogues to our home planet that we have ever discovered, but this world almost slipped through our fingers entirely. When the Kepler Space Telescope first scanned this patch of sky, Its data was processed by automated algorithms designed to catch the telltale dip in brightness as a planet crosses its star. The signal from Kepler 1649c was weak, buried in noise, and the computer program simply overlooked it. It took a second look by human eyes years later to spot the faint pattern that had been hiding in plain sight. That moment of rediscovery turned a forgotten day to point into one of the most promising candidates for life beyond Earth. Because of its size and the amount of light it receives, this planet is often described as an Earth analog, a world that could very well mirror our own in terms of surface temperature and the potential for oceans. But there is a catch. Its star is a red dwarf, a type known for violent flares that can strip away a planet's atmosphere over time. If Kepler 1649c ever had a thick blanket of air, those repeated bursts of radiation may have eroded it long ago. Still, some researchers argue that life could adapt. Perhaps the planet holds onto a thin but stable atmosphere made of heavier gases like carbon dioxide. Or maybe it has a magnetic field strong enough to deflect the worst of the flares. We simply do not know yet. What we do know is that Kepler 1649c sits in the habitable zone, receives the right amount of energy, and is the same size as Earth. That combination is rare and precious. It pushes this world to the top of the list for follow-up observations. And while it is 300 light-years away, that distance is not too far for the next generation of telescopes. The James Webb Space Telescope could already detect its atmosphere if conditions are right. But for now, Kepler 1649c remains a promise, a world that might be our closest twin, hidden until we are ready to see it. Its story reminds us that even in data we have already collected, new discoveries are waiting, and the next planet on our list was not hidden at all. Its signal came through loud and clear, making it one of the most confidently detected candidates for life in the entire galaxy. Not every promising world makes headlines. Some sit quietly in the data, waiting for patient eyes to appreciate their worth. Kepler 1410b is one of those quiet gems, a super-Earth about 1.2 times the size of our own planet. It orbits a K-dwarf star, a type that glows steadily and lives for tens of billions of years, far longer than our Sun ever will. That longevity matters. It means the planet has enjoyed a stable source of energy for a very long time, giving any potential life forms ample opportunity to arise and evolve. The planet sits squarely inside the habitable zone, where temperatures allow liquid water to exist on the surface. Its equilibrium temperature, the temperature the planet would have if it had no atmosphere, is strikingly similar to Earth's own. That does not guarantee warmth. A planet with no atmosphere would be a frozen desert, but it does suggest that if Kepler 1410b possesses even a modest blanket of greenhouse gases, it could be quite comfortable. Its radius and estimated mass hint at a rocky composition, perhaps with a solid surface and a thin atmosphere. We cannot be certain without more data, but the clues are promising. What makes Kepler 1410b valuable is not fame. It is not the closest or the most Earth-like in size. It is instead a representative of the wider population of potentially habitable worlds. Most of the planets we discover are not headline makers. They are ordinary, unassuming, and common. By studying many such worlds, astronomers learn to separate the typical from the exceptional. They ask how many planets at this size actually have atmospheres, how many retain liquid water over geological timescales. Kepler 1410b is a test case for those questions. Its star is bright enough for follow-up observations with the James Webb Space Telescope, though the planet is far enough away that those observations will be challenging. Still, the effort is worthwhile because every data point fills a gap in our understanding. The quiet ones teach us about the full range of possibilities. Some habitable zone worlds may be ocean-covered. Others may be dry deserts with thin carbon dioxide atmospheres. A few might hold exactly the right mix of gases to support life. Kepler 1410b reminds us that the search for life is not about finding a single perfect twin. It is about mapping the diversity of conditions across the galaxy. That diversity becomes even more striking when we consider planets around stars that are nothing like the dim K dwarfs we have been discussing. Some stars burn hotter, brighter, and faster, and their planets face a completely different set of challenges. 850 light-years away, a planet of uncertain nature circles a steady K-dwarf star. Astronomers call it Kepler 440b, and its size sets it apart from the worlds we have seen so far. At roughly 1.9 times the radius of Earth, it sits in a gray zone where composition becomes a critical unknown. It lies squarely within the habitable zone, the region where liquid water could exist on a surface. But that size raises a fundamental question. A planet this large may have held onto a thick envelope of hydrogen and helium, the lightest and most abundant gases in the universe. If that is the case, Kepler 440b would be a mini Neptune, a world with a crushing atmosphere and no solid ground, a place where life as we understand it would struggle to gain a foothold. Yet there is another possibility. The planet could be a water world, a globe covered entirely by a deep ocean with perhaps a few scattered volcanic peaks breaching the surface. In that scenario, the hydrogen and helium would be minimal, and the surface would be liquid water, warm and stable enough to host microbial life. The difference between these two fates depends entirely on the planet's mass. If Kepler 440b is dense and heavy, it is likely rocky with a thin atmosphere. If it is light and puffy, it is a gas dwarf. Astronomers have not yet measured its mass precisely, and that missing piece of data keeps the mystery alive. The planet was discovered by the Kepler Space Telescope using the transit method, which reveals only its size and orbital period. To know its true nature, we need to measure how much it tugs on its star, a technique called radial velocity. That requires sensitive instruments and many hours of observation. For now, Kepler 440b remains a tantalizing unknown, a world that could be a watery haven or a gaseous ghost. It reminds us that size alone is not enough, and that the search for life demands patience and deeper investigation. But not every planet keeps its secrets so quietly. Some worlds reveal their character through the shape of their path, swinging through their habitable zones in ways that defy expectations. One such planet travels an orbit that is not a perfect circle but an elongated ellipse, and that eccentricity may hold the key to understanding its true potential for life. 470 light-years away, a planet nearly identical to Earth in size faces a far more volatile star. Kepler 438b has a radius just 1.12 times our own, and it orbits a red dwarf star that burns with frequent and powerful flares. From the planet's surface, those flares would appear as sudden, brilliant flashes of light, eruptions that release intense radiation across the spectrum. The planet sits squarely inside the habitable zone, the region where liquid water could pool on solid ground. It receives about 40% more sunlight than Earth does, which alone would nudge its surface temperature toward the warmer side. Many astronomers rank this world very high on the Earth Similarity Index, a score that compares a planet size, temperature, and location to our own. But when they calculate their confidence in its actual habitability, the number drops sharply. The reason is the star. Red dwarfs are known for their unstable behavior, and Kepler 438b host is one of the most active of all. Those frequent flares could erode any atmosphere the planet might have formed, slowly stripping away the protective blanket that life depends on. Even if the world once held oceans, the relentless burst of high-energy particles may have boiled them into space long ago. Kepler 438b teaches an essential lesson. Location alone is not enough. Being at the right distance from a star is just the first step. A planet also needs a calm, stable parent that does not threaten its atmosphere with constant eruptions. This world appears almost perfectly Earth-like from a distance, but up close, the conditions may be harsh and unforgiving. The gap between its high similarity score and low confidence rating reminds us that we must look deeper beyond simple checklists to understand what truly makes a world livable. Fortunately, not all stars are so restless. Some burn with a steadier glow, offering their planets a far better chance at holding onto the air they need. One such star lies just 42 light-years away, and the world circling it may finally give us the clear signal we have been searching for. But not every promising world orbits a star that close. 217 light-years away, a different kind of discovery emerged from the extended Kepler mission, a mission that kept scanning the sky long after its primary fuel ran low. That world is K272e, a super-Earth discovered by the K2 campaign, and it offers a fresh perspective on what a habitable planet might look like. Its radius is about 1.3 times that of Earth, placing it firmly in the rocky category, a world with a solid surface where oceans could form. It orbits a dim M-dwarf star, a red dwarf that shines far more faintly than our Sun, and it sits squarely within the habitable zone, the region where liquid water can exist. In fact, measurements show that K272e receives a similar amount of starlight to what Earth gets from the Sun. That is a remarkable coincidence. The planet completes one orbit every 18 days, an incredibly short year, but because its star is so dim, that close distance still provides just the right amount of warmth. Yet being so close to a red dwarf brings a familiar consequence. The planet is almost certainly tidally locked, with one hemisphere locked in perpetual daylight and the other in endless night. Only the narrow twilight ring between them might offer stable temperatures for water. But here is the encouraging part. Astronomers believe that a stable atmosphere could still exist on such a world, especially if the planet has a thick blanket of greenhouse gases or a strong magnetic field to deflect the worst of the stellar flares. K272e is a powerful example of the many candidates found by the extended Kepler mission, a mission that squeezed every drop of data from a damaged telescope and still delivered worlds worth studying. It reminds us that the search for life does not end with the primary mission. Sometimes the most promising discoveries come from a second look, a renewed effort, and a willingness to keep watching. And that persistence has already paid off again. Another K2 campaign, scanning a different patch of sky, revealed a planet that pushes the boundaries of what we thought possible. That planet is called K23d, and it orbits a red dwarf 150 light-years away. It belongs to a three-planet system discovered by the extended Kepler mission, and its size places it firmly in the super-Earth category at 1.6 times Earth radius. Its orbital period is about 45 days, putting it squarely inside the habitable zone where liquid water could exist on a solid surface. What makes this world especially valuable to astronomers is that they have tried something rare. They have attempted transmission spectroscopy on it, a technique that captures the starlight filtering through its atmosphere and reveals what gases are present. Only a handful of habitable zone planets have been studied this way, and K23d is one of them. The early results were tantalizing but not conclusive. The data hinted at the presence of water vapor, but the signal was too weak to be certain. Still, the very fact that we have even a hint of an atmospheric signature is a milestone. It proves that we can begin to probe the air of worlds far beyond our solar system. K23d is not a perfect Earth twin. Its size and the dim nature of its star mean it may be a scaled-up version of our own world, perhaps with a thicker atmosphere and a hotter surface. But the opportunity to study its chemistry moves us beyond simple discovery into the realm of true characterization. The next step will require more powerful telescopes and longer observations, but the path is clear. As the search continues, we turn our attention to a different kind of world, one that takes its time to circle a star that burns much like our own sun. 1,200 light-years away, a lesser-known world quietly earns its place among the promising candidates. Kepler 1544b orbits a K-dwarf star, a type that burns steadily and lives for tens of billions of years, far longer than our Sun. This super-Earth measures about 1.7 times the radius of our planet, placing it in the category of rocky worlds that could hold onto a thick atmosphere. Its orbital period of 168 days means its year is roughly half as long as Earth's, and the distance from its star puts it near the outer edge of the habitable zone. At that distance, it receives only about 50% of the sunlight Earth gets from the Sun. That is not a lot of energy. Without help, surface water would likely freeze solid. But help may come in the form of a greenhouse effect. If Kepler 1544b has an atmosphere rich in carbon dioxide or methane, those gases could trap enough heat to keep liquid water stable across at least part of the planet's surface. A thick blanket of air could push temperatures above freezing even at this chilly distance, turning what would otherwise be a frozen world into a temperate one. The planet does not grab headlines like some of its flashier neighbors. It was discovered by the Kepler Space Telescope and quietly catalogued among thousands of other candidates. But that obscurity does not diminish its potential. Astronomers consider it a solid, if less discussed, candidate precisely because its size and orbit fall within the range where surface liquid water is plausible. It represents the many promising worlds that do not make the front pages but still deserve serious study. Every such candidate adds a data point to our growing map of habitable conditions. Kepler 1544b reminds us that the search for life is not just about the obvious Earth twins. It is also about the quiet worlds at the edges, where conditions hang in a delicate balance, waiting for the right atmosphere to tip them toward livability. And that balance becomes even more intriguing when we consider a planet orbiting a star so ancient it has been shining for nearly the entire history of the universe. 2,800 light-years from Earth, a star older than our Sun shines steadily. That star is a G-dwarf, the same type as our own, and it hosts a planet remarkably close to Earth in size. Kepler 1638b measures about 1.1 times the radius of Earth, making it a near twin in scale. It completes one orbit every 259 days, a year that falls comfortably within the habitable zone where liquid water could pool on a solid surface. But what makes this world especially intriguing is its star. Our Sun is roughly 4.5 billion years old, still in its middle age. The star of Kepler 1638b is significantly older, perhaps 6 or 7 billion years, and it has long since settled into a quiet, stable phase. Younger stars tend to be more active, spinning faster and unleashing frequent flares that can strip away a planet atmosphere. An older star, by contrast, has calmed down. Its rotation has slowed, its magnetic activity has diminished, and it pours out a steady, predictable stream of light. For a planet orbiting in the habitable zone, that stability is a gift. Without violent eruptions eroding the air, an atmosphere can persist for billions of years, giving life a long, uninterrupted window to emerge. Kepler 1638b is often described as an analog for early Earth, not because it is identical, but because its size and orbit place it in a similar physical situation to what our home world faced billions of years ago. If we could study its atmosphere, we might catch a glimpse of a planet in a stage that mirrors our own distant past, a young rocky world perhaps covered by oceans, with clouds and a greenhouse effect that keeps temperatures mild. The planet's star is also slightly dimmer than the Sun, which means the habitable zone sits a little closer in. That 259-day orbit is not too short and not too long, just right for a climate that could be temperate. Astronomers pay close attention to stellar age because it directly affects a planet's chance at developing and sustaining life. A star that burns steadily for tens of billions of years provides a stable energy source and a safe environment. A star that flares violently or brightens too quickly can doom any biology that might have started. Kepler 1638b offers a reminder that the best candidates are not always the closest ones, but often the ones with the most patient parent stars. What secrets might such a world hold about our own planet's deep history? We may learn more as telescopes improve, but not every promising world basks in the glow of a sun-like star. Some circle stars so faint and cool that their habitable zones lie extremely close, where the light is dim and the challenges are different. 2,500 light-years away, a K-dwarf star hosts a super-Earth named Kepler 443b. Its radius is 1.5 times that of Earth, placing it comfortably in the category of rocky worlds that could hold onto a thick atmosphere. The planet completes one orbit every 177 days, a year that sits inside the habitable zone of its star, the region where liquid water can exist on a surface. But there is a catch. Kepler 443b receives only about 65% of the sunlight that Earth gets from the Sun. That is a stark difference. To put it in perspective, that is roughly the same amount of solar energy that Mars receives from our own star. And we know what Mars looks like today, a cold, dry desert with a thin atmosphere and frozen water locked in the ground. Yet Kepler 443b might not share the same fate. The key is its atmosphere. If this world has a thick blanket of greenhouse gases like carbon dioxide or methane, those gases could trap enough heat to raise surface temperatures far above what Mars experiences. A thick atmosphere acts like a thermal blanket, holding onto warmth that would otherwise escape into space. With enough greenhouse warming, liquid water could persist on the surface even at this chilly distance. The planet could be a temperate world, perhaps with oceans, clouds, and a stable climate, despite receiving less than 2/3 of Earth's sunlight. That possibility places Kepler 443b in a category astronomers call a marginal candidate. It is not a clear, sure thing like some of the worlds we have seen. It sits at the outer edge of the habitable zone, where the margin between a frozen world and a living one is razor-thin. The uncertainty around such planets is enormous. We do not know the exact composition of its atmosphere, if it has one at all. We do not know if it formed with enough greenhouse gases to compensate for the low light. We do not know how its star behaves over long timescales. All we can do is model the possibilities and wait for better telescopes to provide real data. These marginal worlds are incredibly valuable because they define the boundaries of habitability. They force us to ask just how much greenhouse gas is too much. How little starlight can a planet receive and still support liquid water? Every borderline candidate sharpens our understanding, and as we refine our methods, we look for planets that offer greater stability, worlds whose orbits are nearly circular, with minimal variation in distance from their star. One such planet stands out for having one of the lowest orbital eccentricities ever measured, a steady path that promises a remarkably stable climate over billions of years. A perfectly circular orbit is rare, but when a planet settles into one, its climate stays remarkably consistent, season after season, for billions of years. Kepler 283c enjoys that kind of steady path. It sits 1,200 light-years away, circling a K-dwarf star that glows with a calm, reliable warmth. The planet itself is a super-Earth, roughly 1.8 times the radius of our world. That puts it in a size range where composition becomes a fascinating question. It could be rocky, with a solid surface and perhaps mountains and valleys, but its relatively large radius suggests something else entirely. Astronomers suspect Kepler 283c might be a water world, a planet covered by a global ocean so deep that no land breaks the surface. The planet completes one orbit every 92 days, placing it firmly inside the habitable zone where liquid water can exist. But it receives only about 60% of the sunlight Earth does from the Sun. That is a modest amount of energy, similar to what Mars gets. Yet if the planet has a thick atmosphere rich in water vapor or greenhouse gases, that blanket could trap enough heat to keep the ocean from freezing. Imagine an endless blue sphere with waves rolling endlessly under a dim red sun and clouds wrapping the entire world in a warm, steamy shroud. That is the picture some astronomers paint for Kepler 283c. It was discovered early in the Kepler mission, and while it never captured headlines like some of the larger or closer worlds, it has remained a steady subject of interest. Its stability, its size, and its position in the habitable zone all make it a valuable data point in the growing map of potentially habitable planets. The world quietly waits for better telescopes to peer through its clouds and reveal whether those oceans truly exist. And from these early Kepler discoveries, the search expanded to include planets found by a completely different method, one that does not rely on dimming starlight but instead measures the subtle gravitational dance between a star and its worlds. The HARP survey, a ground-based project using high-precision spectroscopy, has uncovered several promising candidates that lie close enough for detailed study. 16 light-years from Earth, another world emerges from the data of that same survey. It is called Gliese 832c, and it was discovered by watching the star wobble under its gravitational pull, a technique known as radial velocity. This super-Earth has a mass roughly 5 times that of our own planet, placing it in a category where astronomers cannot be certain what lies beneath the surface. It could be a mini Neptune, a world wrapped in a thick envelope of hydrogen and helium with no solid ground for life to stand on. Or it could be a dense rocky planet, perhaps with mountains, oceans, and a thin atmosphere that allows liquid water to pool on its surface. The orbit of Gliese 832c hugs the inner edge of its red dwarf star's habitable zone, a region where the light is strong enough to keep water liquid but only just. Because the star is so much dimmer than our Sun, that habitable zone lies very close in. The planet completes one orbit every 36 days, a short year that keeps it locked in a tight, steady path. Being so near to its star brings a familiar risk. Red dwarfs are prone to powerful flares that can strip away a fragile atmosphere over time. Yet the star's relative calm gives astronomers hope. The real prize is proximity. At just 16 light-years away, Gliese 832c is one of the closest known super-Earths in the habitable zone. That makes it an ideal target for future direct imaging missions, telescopes that can block out the star's glare and capture the planet's own faint light. Those images could reveal its color, its weather patterns, and even the seasonal changes of its cloud cover. For now, the planet remains a mystery wrapped in conflicting data, a world that could be a barren gas world or a rocky haven. The next generation of instruments will decide, and the search for nearby candidates does not stop here. Another world, even closer, waits for its story to be told. 14 light-years away, a super-Earth orbits a quiet red dwarf star. This world, Wolf 1061c, is one of 3 planets discovered in its system, but it holds a special place in the search for life because it sits squarely within the habitable zone. Its mass is about 4.3 times that of Earth, placing it in the super-Earth category, a rocky world large enough to hold onto a thick atmosphere if conditions allow. The planet completes one orbit every 18 days, a short year that keeps it very close to its dim parent star. That proximity brings a familiar consequence. Wolf 1061c is almost certainly tidally locked. One hemisphere always faces the star, locked in perpetual daylight, while the opposite side remains in endless night. Only the narrow ring between them, the twilight zone, might offer a stable temperature range where liquid water could gather. But the implications of tidal locking for climate are not as simple as they first appear. Some scientists argue that with a thick enough atmosphere, heat could circulate from the day side to the night side, smoothing out the extreme temperature differences. A global wind pattern could transfer warmth, preventing the night side from freezing solid and the day side from boiling. If that circulation is efficient enough, the entire planet might be habitable, not just a thin strip of twilight. That idea is still debated, but it raises the possibility that Wolf 1061c could support a stable climate across much of its surface. The planet's proximity, just 14 light-years away, makes it one of the closest known potentially habitable worlds. Its star is dim but relatively calm for a red dwarf, though not as quiet as some of the more stable stars we have seen. Telescopes like the James Webb Space Telescope and future ground-based observatories could study its atmosphere in the coming years, searching for water vapor, carbon dioxide, or the subtle signs of biological activity. Wolf 1061c is a reminder that the closest candidates often come with their own set of challenges: tidal locking, flare activity, and atmospheric uncertainty, but they also offer the best chance for detailed study. And from this nearby world, we turn our attention to a planet whose host star has been studied more thoroughly than almost any other in the search for life. Just 11 light-years from Earth, a remarkably quiet red dwarf hosts a planet almost identical in size to our own. Astronomers call it Ross 128b, and its radius is about 1.1 times that of Earth, placing it squarely in the rocky category. It orbits its star at a distance that receives roughly 1.4 times the sunlight Earth gets from the Sun, which puts it comfortably inside the habitable zone where liquid water could persist on its surface. But what makes this world stand out from the crowd of red dwarf candidates is not its size or its orbit. It is the star itself. Most M-dwarfs are temperamental, unleashing powerful flares that can strip away a planet's atmosphere over time. Ross 128b host is different. It is one of the quietest red dwarfs ever studied, with such low flare activity that astronomers call it inactive. That calm temperament is a game changer. Without the constant threat of radiation stripping away its protective blanket, Ross 128b has a much better chance of holding onto the atmosphere it may have formed with. A thick atmosphere could trap heat, stabilize temperatures, and shield the surface from harmful particles, creating an environment where liquid water can remain stable for billions of years. For a world that is both close to us and bathed in just the right amount of starlight, this combination of size, orbit, and stellar stability is rare. That is why Ross 128b is ranked among the top targets for atmospheric characterization with the next generation of telescopes. The extremely large telescope and the James Webb Space Telescope could soon analyze the light filtering through its air, searching for water vapor, carbon dioxide, or even the faint chemical signatures that might hint at biological activity. If any of those gases are present in abundance, Ross 128b could become our clearest window into a living world beyond the solar system. Its proximity makes follow-up observations feasible. Its quiet star gives it a fighting chance, and its Earth-like size makes it a natural place to look for life as we know it. But not every promising candidate orbits such a steady sun. Some worlds circle stars so faint and dim that their very existence was hidden for years, waiting for more sensitive instruments to finally detect the tiny signal of a planet in the habitable zone. 6 light-years away, a solitary star holds a world at the edge of possibility. This is Barnard's Star B, a super-Earth with a mass roughly 3.2 times that of our own planet. It orbits the nearest single star to the Sun, a dim red dwarf that has long fascinated astronomers for its steady motion across the sky. The planet lies near what scientists call the ice line, the boundary where temperatures drop so low that water would freeze solid even under an Earth-like atmosphere. That places it within the optimistic habitable zone, the region where liquid water could exist only if the planet has a very thick blanket of greenhouse gases to trap heat. Without such an atmosphere, Barnard's Star B would be a frozen world, its surface locked in eternal ice. But a thick carbon dioxide or hydrogen atmosphere could change everything. If the planet formed with a massive envelope of gas, the greenhouse effect might raise surface temperatures enough to allow liquid water in certain regions, perhaps even a liquid ocean hidden beneath a layer of ice or a warm twilight zone along the edge of the tidally locked day-night boundary. The detection of this world was a hard-fought victory. Barnard's star is tiny and dim, barely glowing with a fraction of the sun's light. Spotting the minute gravitational tug of a planet around such a faint star pushes our instruments to their absolute limits. The signal was so subtle that some researchers initially doubted its existence, arguing that the apparent wobble could be caused by the star's own magnetic activity. But after years of careful observation with multiple telescopes, the consensus shifted. Barnard's star B is now regarded as a strong candidate, though its exact properties remain uncertain. The controversy itself is valuable. It shows how challenging it is to find and confirm planets around the smallest stars, which happen to be the most common in the galaxy. Every confirmed or debated detection teaches us how to refine our methods and separate true planetary signals from stellar noise. Barnard's star B stands as a testament to persistence, a world that might be just cold enough to demand a second look, but just warm enough to keep hope alive. As we approach the end of this journey, the next world on our list offers something truly different, a planet that might finally settle the biggest question of all. 41 light-years away, a planet offers scientists exactly what they need for a clear, confident study. This world is LHS 1140b, a super-Earth that orbits a quiet red dwarf star, one of the calmest M-dwarfs ever observed. Its mass comes in at 6.6 times that of Earth, while its radius stretches to 1.4 times our planet size. That ratio of mass to radius tells astronomers something crucial. The density of LHS 1140b is higher than that of a gas giant but lower than pure iron rock, pointing toward a rocky composition wrapped in a thick atmosphere. This planet transits its host star, meaning it crosses directly in front of the star from our line of sight. That simple alignment opens a door that many promising worlds never offer. When a planet transits, starlight filters through its atmosphere, carrying the chemical fingerprints of whatever gases are present. Astronomers can break that light apart, molecule by molecule, and read the planet's air like a book. Water vapor, carbon dioxide, methane, even the faint signs of oxygen might reveal themselves if conditions are right. LHS 1140b sits comfortably inside the habitable zone of its star, receiving enough starlight to keep liquid water stable on its surface, provided that atmosphere traps the right amount of heat. Its host star burns with such steadiness that the planet has likely enjoyed billions of years without violent flares stripping away its protective blanket. That combination of calm star, transiting orbit, and Earth-like density has made LHS 1140b one of the most intensely studied super-Earth candidates in the entire exoplanet catalog. Telescopes on the ground and in space have observed it over many orbits, building up a detailed picture of its size, mass, and orbital path. The James Webb Space Telescope has already taken a look, and early data suggest the planet may hold onto a significant atmosphere, perhaps one rich in water vapor or nitrogen. If those hints prove true, LHS 1140b could become a benchmark world, a place where we can test our models of how rocky planets evolve and how life might arise under different conditions. What sets LHS 1140b apart from many of the candidates we have explored is the level of confidence in the data. There are no marginal signals or overlapping stellar noise. Its mass is well measured, its radius is precise, and its orbit is stable. This planet represents the high-confidence end of the sample, a world where the uncertainties narrow rather than widen. It gives us a solid anchor point in the search for life. As we approach the final world on this journey, one thing becomes clear: the universe is not silent. It is filled with rocky worlds circling stars of every kind, from violent flares to steady glows, from frozen edges to temperate sweet spots. The next great leap will come when we point our telescopes at these worlds and wait for the light to carry its secret home. After exploring 30 worlds, a clear pattern emerges across the stars. Stellar type matters more than almost any single factor. Planets around calm, stable G and K dwarfs like our own Sun tend to offer the safest long-term havens for life. Super-Earths appear not as rare exceptions but as the most common kind of potentially habitable world, a reminder that the galaxy favors sizes slightly larger than our own. And the constant refrain throughout this journey has been the need for better data. We can measure a planet's size and orbit, but its atmosphere, its true character, remains hidden until we can read the light filtering through it. That is where the greatest uncertainty lies and also the greatest promise. The universe appears to be filled with worlds that could support life, but our knowledge is still a thin layer on a deep ocean of possibility. Every new discovery from the James Webb Space Telescope, every observation from ground-based observatories like the extremely large telescope, pulls back that veil a little more. The search is accelerating, and the next few years could bring revelations that reshape our understanding of our place in the cosmos. So stay curious. Watch the skies, follow the missions, and keep asking the big questions. If this video sparked your sense of wonder, please like and subscribe to join us on future explorations. And drop a comment below telling us which of these 30 worlds you find most promising. Is it the quiet neighbor Lytton B, the ocean world TRAPPIST-1F, or the ancient steady glow of Kepler 1638b? Your voice adds to the conversation. As we close this journey, one thought lingers. We may be closer than ever to answering the most profound question of all. Are we alone? The hope is not just that the answer exists, but that the next generation of telescopes, built by human curiosity and ingenuity, will bring that answer into the light. Until then, the stars keep their secrets and we keep watching.